Welcome all of you for this course on river engineerings. And if you look at this course, already we discussed about bridge scour. Today we will further discuss about jet scour, as well as we will also discuss about the national waterways, or how we can have a advanced technology for navigating the rivers or the national waterways. So, that the concept we will discuss more detail today, and looking that I will have a emphasize now we are following these books, which is having a chapter on river engineerings. That part what we are following it here, as well as you know it, those are the books. Also we have lot of reference on that. Now, if you look at that, today what we will cover it, jet scours, we will cover about waterways, talk about some of the very relevant case studies, and I also will talk about the locks and dams, and also the dredging. So, those are the concept today we will discuss, that how we can do the dredgings to maintain a river channels for navigation's point of view or other utility point of view. We can also look for a option for dredgings. Those things we will discuss today more detail. Looking for the first part, jet scours. Let us look at these 4 figures, which gives very interesting things, that what type of scour can happen it. Like if you have the dam, you have the dam structures, and you have the water jet here. Because of the water jets, the initially whatever the soil part, that what will be scour it, and you can see there is a vortex patterns what will be created in, and that vortex will be dissipated as go up. So, if you look at that, it also depends upon theta jet, the angle of jet, water jet, what is impinging on the waters. It also depends upon the tail water depth, how much of the depth, water depth at the tail water levels. It also depends upon the bed materials, what type of bed materials are there. So, this is the scour happens it just the downstream of a dam or the west, where you have a water jet impinging on a tail waters. We need to find out what is the scour depth, delta z, the scour depth, and you can see the process. The mostly again we go for the physical model and establish the relationship with this delta z with the flow, with the water depth at the tail end, the bed material characteristics. All we do it with function of h. We try to establish the relationship with the delta z with the functions of all this part. That is what we look at when you talk about this. As we discussed for the scour in bridge spire, the same concept also followed it, the plunging jet scours, that part what also follow it. Same way, if you look at many of case, you can have the dam structures and you can have a sluice gate. As you have the sluice gate, and that the sluice gate will have a V1 velocity and yj depth, and you can understand it how the scour mechanism is going to form it here, okay. And there will be scour depositions, and because of that we try to know it what will be the scour depth, delta z. What is the scour depth? Is a functions of V1, V2, yj and the bed material. At the bed material, again the similar way, conducting a series of physical experiments, scale down models, and try to establish the empirical relationship between the flow characteristics with the scour depth. That is what the basic idea is there. But many of the times you can have a grade control structure scours. That means, you may have a higher level of, then you may have the low level the scouring materials. It can happen in the rivers. You may have regions where you have stones followed by you may have the sand. Because of that, if this stone and sand, or if you have a weir and the river bed, you can have the grade control structure scour. Okay. So, you will have the scour, because as the flow the vortex and generates in it, and this is what the scour it, and here you will have a deposit mode. That means, whatever the scour materials also deposit here, and then you have the tail end depth, V2 velocity and V1. So, just try to understand the conceptually how the process happens, how the scour depths are happening. And most of the times we conduct the series of physical experiments, and then we establish the relationship between delta z with the hydrodynamic parameters like the velocity, theta z, the ht, the tail end depth, as well as the flow velocities. Those empirical equations are really necessary for us to know it, how we can effectively design a hydraulic structures like a weir, or having a gate with a sluice gate, or you have a graded control structures, or you can talk about the culverts. So, many of the times we do not bother about the culvert scours, but culverts also have a scour during stream flood events. During stream flood events, you can have the scour depth. That is the things I used to there, that you have to understand it, there will be the scour when you have the culvert. Even if you have the culvert, like if you look at the culvert can make a water jet. When you have a very high flow, the Q amount of discharge is going into that, it can create a jet, and that jet can impinge it and create the bed scours. So, just downstream of the culvert we can have the scouring, and we should, whenever we design the culvert, we should take care of how we have to protect the scour, or what should be the strategy for scour countermeasures, that we should do it. So, if you look at these culvert scours, which is depends upon the diameters, the discharge and the flow patterns, what is happened, that is the delta z is a scour depth, and you have the flow. So, in summary I can say that the scour jet scours happens in case of plunging case, that means you are impacting, plunging it inside a tailwinders, or it can have a submerged jet scours, it can have a culvert scours or grade control structure. So, now let us come to the empirical equations, which is derived by conducting a series of lab experiment or the physical experiment, the scale down experiment setups. Now, if you look at first ones, that is what basically we release the water periodically and the downstreams, and the plunging jets or submerged jets needs to be considered, okay, to look at the stability analysis of hydraulic structures. Okay. And if you look at that, the Phelps boats 1994, he established the relations with the scour depth with B1 velocity of z velocity, theta j stands for the angle measured to horizontal at the water surface, the jet angles which is measured from horizontal at the water surface. Then you have the depth, the tail end water depth, and you have a Kp stands for here the coefficients for plunging jet. So, that is the reasons if you look at it depends upon jet characteristics in terms of the jet velocity, theta jet, it depends upon tail water depth. That is why if you have higher the tail water depth, you will have a delta jet is less. That is what is most of the times is there, that they create a stilling basins or can have another control structure such a way that we can increase the tail water depth and we can reduce the scouring depth. That is what is being followed many of the downstream of a bridge or the downstream of where when you measure that we try to have the tail water depth So, if you have a tailwater depth is sufficient, you can know is scour depth will be that, and this Kp depends upon the bed material characteristics. Kp depends upon bed material characteristics, and you can look it, these are what it all depends upon the sin theta j. Q is the flow rate per unit width, flow rate per unit width. So, what I am to say is, if you look at the empirical equations, always we try to understand it, and that understanding will give us a guiding principle how to manage that hydraulic structures during the scour formation, extreme flow conditions. That's the biggest idea, that if you have very extreme flow conditions are coming, we need to have the tail end water depth at the major bridge dam locations or the weir locations, such a way that we can reduce the scour depth. Next one is that we can look at how we can have a Kp value variations. If you look at that, the Kp is a plunging coefficient, is a multiplication factors, that is what you try to understand it, which is a 20 for the silt. So, in the downstream, if you have the silt, this factor is 20, 5 to 20 the range for the sand, and you have a gravels is a 3 to 5. So, you just interpreted it that if you have the silt, the scouring depth will be 20 times or the almost 10 times, close to the 10 times as compared to the gravels. So, what it indicates from this experiment data, so we can know it what type of downstream bed materials we can either armoring it or we can put it such a way that we can reduce the scour depth. That is what is here. So, you can see that if you have a gravel, so this coefficient is just range from 3 to 5, but in case of the silt it is as high as the 20. So, that is almost 8 to 9 times higher, that is what it happens in case of the silt and the gravels, because the more the scour depth, it will be the dangers to the hydraulic structures, because that the depth it will go, and again I am to repeat it, the extreme scours happen during the extreme floods. So, we do not know it what type of flood is going to come it, and that period how we do manage it, what could be our strategy to look at the safety of the dam and the weir structures, because we have to protect the scouring mechanisms, protect the scour holes. To protect the scour holes, we should have this knowledge of the scouring, that how we can manage it with the gravels or tailwater depth. That is the, so that is the reason the summer jets entirely under the free surface flow under the sluice gate. So, if you have the sluice gate, you would also have the considerable scouring potentials. Okay, that is what the Hoffen-Benhertz 1997 established the equilibrium scour depth. It follows the Newton's second laws. This is we have been discussing about applying the linear momentum equations in a contour volume, exactly same concept with using a coefficients. It has find out that delta z is a function of y j is a inflow, z thickness, depth, k s j is a scouring coefficient, again it is a depends upon the bed material characteristics, and V 1, V 2 are inflow and outflow velocity respectively. So, if you look at that, again if you look at that k s j, it varies from the 50 to again this range of values for the gravels and for the sand and for the silts. So, you can see that you have a bed materials in different like a silt, sand or the gravels, the scouring you can know it what is happening. Now, let us come to the scour below the grade control structures. There is a drop structures. Okay, that was we are talking about that. I have a grade structures, below that I have the materials. Okay, as it said Z is happens it how we can estimate the Scour depth, how we can estimate the delta Z, the Scour depth. So, if you look at that, again the same experimental works, but the equations looks bit lengthy, but if you look at that, delta Z is a function of sin phi, phi j, g is specific gravity of the bed materials, you have a q, v1 and the d phi. Okay. So, it is a complex equations, but it is not that complex today's world. If you look at that, the dp is a drop height of the grade control structures. The dp is the drop of the, if you look at the figures here. So, dp stands from the this part, theta z is the impinging angles, you have a v1, the velocity, v2 velocity, you have a tailwater depth, then you have a original bed. So, looking this, you can understand it that we can have a relationship between the Scour depth with a functions of dp, the ds, that is what particle size distributions d50 most of the times we consider it. Then you have a theta z, v1 and q. v1 is a unit discharge, discharge per unit width, v1 is approach velocity, ds is a particle size and g is a specific gravity of bed materials and phi is angle of repose of the bed materials. Theta z is z angle measured from the horizontals. So, if you look at these are all the experimental studies plus the dimensional analysis to establish these empirical equations. Okay. So, that is but these relationships tell us that what type of the dependencies of the Scour hole depth in terms of the flow characteristics, in terms of the drop height, in terms of the bed material characteristics. That is what have these things. Now, if you look at that Scour below the circular culvert outlets, okay. Many of the times we generally avoid it, we do not bother about the scouring mechanisms for a culvert, but I do believe it. Many of the time whenever you have a 10 years or 20 years floods, most of the time the culvert fails it, and that is what is a lifeline of a road networks. And during the flood, when it fails it, all sort of the problems we face it because of the floods, not because of the waters, because of failure of the culverts. So, whenever you design the culvert designing, that time we should consider what amount of the scouring happens it during the extreme floods. That is the basic idea. So, if you look at this q is the discharge, d is the diameters for the circular outlets, this is the scouring depth. So, as the d is the culvert diameters, q is a discharge, etc. So, the basically we always have these empirical equations to estimate the Scour hole depth, but whenever we go for a major structures, we conduct a separately the physical modeling studies followed by the dimensional analysis from the case to case, because that is what is gives us the more the field data and the laboratory data, we combine it and we try to modify these equations or try to look at whether these equations are enough for designing scour holes, how to protect the scour holes in major structures like a dam, like culvert, like you have a sluice gate or the grade controls. That is the things. So, let us give for a very simple examples what is there. Let us see, you have a broad crested weir which is built across a 30 meter wide river. It has a drop height is 2.25 and the phase angles of the structure is 60 degrees, that is what is given it here, the 60 degrees, and the Scour hold approximately 1:2 non-cohesive materials. Okay, it is a non-cohesive materials having D50 2 mm, D90 2.5 mm. Estimate the Scour depth when the river discharge is 150 meter cube per second. This is very simple problems, only we have to give it the basic things. So, as you have this where it will have a critical flow depth is here. So, that is you know from the critical flow concept. So, you will have the critical flow here. So, that we need to compute what is the critical flow at this, and there will be some sort of hydraulic jump formations, then followed by this. So, we need to compute the Q, discharge per unit width, we have the drop height, ds is given to us, theta z we compute it as the impingings, that we have a phi value 40 degrees, okay, and we have a g equal to the 2.65, and we try to compute first the critical depth, that is what is commits the critical depth. That is what we discussed earlier, how to estimate the critical flow in terms of flow Proud number is equal to 1, and we can substitute this B is equal to Q by H. Okay. So, you can compute it these equations at the critical flow, which will come it with a flow Proud number is equal to 1. So, you can compute it easily, just to remember these things we can compute it. Now, if you look it, if you go for, so V 1 is we are getting the V 1 for the critical depth, then we are just substituting these values, okay, as it is given it to estimate it what will be the delta z. So, here it comes out to be 5.14 meters, and this is the what the drop height. This is what the drop height is there, and we are computing it what will be the Scour depth. Okay, let us come to very interesting topics. What we are talking about, that is national waterways. You all know about national highways. So, similar way we have national waterways. It starts from national waterways 1, the Ganga rivers from Haldia to Allahabad. So, Haldia to Allahabad, we have the river systems what we can use it. We have been using it as a national waterways 1 to transport the good from Haldia to the Allahabad, and that is what is covers the state like UP, Bihar, Jharkhand and the West Bengal. Same way we have a national waterways 2, that is what is the Brahmaputra rivers from Dhubri to Sadia, which is about 891 kilometer length. So, that is the national waterways starting from Sadia to Dhubri. We also have a national waterway 6, which is connecting for the Barak rivers 121 kilometers. We have a national water 5, which is a Brahmini projects. That is what we demonstrated you as mathematical modeling of Brahmini river is a part of this national waterways 5 projects, where we have a Brahmini and the deltaic regions. That is what is the national waterways 5. Then we have a national waterways 2, which is in the Andhra Pradesh, Godavari, Krishna and the canal systems. That is a combined systems of connecting from Pondicherry, Kakinada, all these are connectivity with the Godavari, Krishna and this, that is what is 1000 kilometers, and it covers the state like Andhra Pradesh, Tamil Nadu and also the Puducherry. So, if you look at that, this is for the national waterways 4. Then similar way we have a national waterways 3, which is the east coast canal, sorry, it is a west coast canals, which is around 205 kilometers. So, if you look at these national waterway systems, what we need is that to have a navigables, we need to know always have the waters at least a minimum water depth, that is a minimum water depth should be there, the river should be navigables. That is not always possible to have that, and what way we can maintain our these national waterways such a way that all throughout the seasons, throughout the years, we can have a the ship, the vessels can go through these channels, they goes through these national waterways. These are very challenging tasks for us, because as you know this river morphology changes it, and the river is quite dynamics, and maintaining the water depth and all are the bigger issues. Okay. So, looking that, let me I talk about the context that to navigate the river, to have enough water to maintain as a national waterways, you need to require for the commercial navigations to for the goods from one point to other points. For example, from Haldia to the Allahabad, we need to have a channel depth and the channel width. The sufficient depth should be there, sufficient width should be there, such a way that the ship, the vessels can start from the Haldia and can go to the Allahabad, or can start from the Dhubri, can go to the Sadia. So, we need to have a minimum the standard channel depth and the width, such a way that river will be the navigable, or the commercial navigations can be done. So, that what we look at that, it also depends upon the factors like the type of volume of the tonnage, what is the goods carrying is there from one point to others. It is just a transport processes, we should know it, how much goods we need to carry from A point to B point and B point to A point through national waterways. We should know this what type of vessels we are using and what is the size of vessels, and tools in generally used to connecting these waterways. So, the basically let us try to understand it, how this national waterways we have, and how we need to make all the national waterways are the commercially navigable. Okay. And that is the reasons we should know it, what is a required channel width should be required and channel depth is required throughout the years, and that all depends upon the what type of goods we are having and what is the volume of that, the type and size of vessels and tools connecting the waterways. Now, if you look at the next point, there are the birds are there, which is carrying the goods from one point to other point in rivers or the canal transports for the transporting the bulk goods. One is open hopper birds. So, if you can see that this type of birds can be good for the carrying openly, that means open deck, it can have a mineral, it can have the coal. So, the length is 175 feet, breadth will be 26 feet, the draft, the depth of the water requirement for to carry to have the shipping through this river, it's needed 9 feet. Okay. So, 9 feet depth. So, you can understand it needs a 9 feet depth and the carrying capacity is 1000 tons. Same way it can have a super jumbo, which is a 250 to 290, length is more, the width or the breadth will be 40 to 90 and it can carry as much as 3000 tons. Okay. So, you can compare with a particular trucks, okay, it carries about 6 ton to 12 ton. So, as equivalent you can compute it how much of goods we can carry in a bulks open hopper birds which can carry from 1000 to the 3000 ton. And as you know it, it's more fuel efficient, no environmental pollutions systems. Okay. But there are the issues, but so if you look at that way, you can see that as equivalent how much ton of materials we can carry it having a standard or the super jumbo, which will carry as high as 3000 tons. But nowadays you have this integrated chemical and petroleum parts. So, here the basic idea to carry the chemicals and the petroleum things, which can have a length 150 to 300, width will be 50 meters, 50 feet, draft need is 9 feet, and the capacity can vary from 1900 tons to 3000 tons. Same way, if you look at covered hopper berths, okay, the standard one is 175 length, 26 width, draft feet is 9, it can carry the thousands. And there are the two boats, okay, which will have you will have a length, breadth, depth and the horsepower needed. So, the basically what I am to do that there are different type of inland vessels are there, and depending upon our requirements, whether you need a open or covered hoppers or integrated chemicals and petroleums, it can have it, and you know it is much fuel efficient, environment friendly inland transport mechanisms, but that is the way that we can carry as much as the 3000 tons. So, that and it goes to the 3000 tons of goods we can carry from point A to point B through the rivers, okay, which it happens in many of the developed countries like United States, any Europe countries, they extensively we use the inland navigations to carry the goods from A to B using the river navigations or the inland navigations. Now, if you look at that, that is what I discuss is that open hopper bridges, the transporting the coal, sand, the gravel and the sulphurs. You can covered hopper beds because it could be a grain, mixed cargo, and the tank beds for the petroleums and the chemicals. Okay. It needs channel alignment, whether it is a straight channel river, okay, or it is a meandering channels. We cannot have the straight channels. Okay. We need to know how you to do it. So, for the straight channels, the what is the alignment is there? What type of is a straight channel? That is you know it. For a river, it's if a canal, it can have a straight channels. For a rivers, we will have a some degree of the meandering, and that is the reasons we should have the strategy for that. Size of the tow, whether one way traffic or the two way traffic, we can plan it as you plan for national highways. We can think it that whether you have a one way traffics or the two way traffics, that what we can plan it. So, one way traffic basically we can have the signaling systems, you can have the also look at the good visibilities and all the things. So, one way traffic you have to know it, how much visibility we are happening it. The two way traffics, it heavy traffic to move fast, but tows are meeting or the passing part. So, basically we try to know it as when you going through this thing, how this tow spacing and it is giving it in case of the river meanders, river bends. The wider navigation channels we required it for bends which takes the oblique positions. The river in a bend, the navigations vessels will have a oblique positions. For that we need a wider channels as compared to the straight channel. Navigation channel is width is a direct proportion, so with drift angles. We will show it and we will discuss more. Look at the next figures. What is the width is necessary? It is very simple figures. If you look at one way traffic, it is a tow, then you need to have a 40 feet both left and right side. But if you have a two way traffics, you need to have a 20 and 50 feet, then you will have the both the tows. Okay. So, this is for the straight channels. As I said it, the straight channel is possible for only the man-made canals, but the rivers we may not have the straight reaches. So, we always have a bend. So, if you look at this figure, you can understand it that when you have a radius of curvature is 3000 feet, degree of curvature is 90, the velocity is 3 feet per second, and if you have that, so it is from the P.J. Julian books. If you look at that, how the deflections angles are changing it and the channel width requirement. So, you can, if you have a two arrangement, you can see that as the vessels goes and how these the deflections angles are changing it and how the channel width requirements is changing it. That is what is showing to you. Okay. So, that is the compositions, it is showing from difference width requirement for different angles, and we also have a difference toe length, toe width and the length. That is what is showing it that the drift angle is a larger in downbound tools than the upbound tools, that varies it. The radius of curvatures, it depends upon the speed, power and design of the craft, wind force. The toe is empty or the loaded, the traffic is going up or down, all we do it, and the flow patterns. Many of the times we do a physical models, try to know it, if the ship vessels are coming with a toe, that how things are happening, whether it can smoothly pass it without having any impact on the river banks. That is the canal bend. So, that is the we do a physical models, try to know it, the scale model try to know it, whether it will be navigables with a particular river bend and what could be the width requirement and the deflections angles. Now, if you look at the next part, the many of the times we have to make a river its alignment, either a mild river bend or we can have the straight channels. The river, as you know, it does not follow exactly straight path, we have to confine the rivers. We have to make it fairly straight channels or the bend with a larger radius of curvatures. Okay. That is our idea for a channel to make navigables. So, wider channel waterway alignment can be controlled through revetment. You can see this revetment, you can have a many places you can see the revetment, the structure protecting in the river bank. And as we discussed earlier, so you can have the revetment, you can have a spot dikes to divert the flow, you can have the spot dikes, you can see this figure, you can have the spot dikes to divert the flow from the bank and confining the flow, or you can have a stone riffraff, you can see these figures. Okay. And if you visit any rivers which is a navigable rivers, you can see that stone riffraff, the revetment nowadays. You can have a longitudinal dikes, the construction of revetment, spot dikes, as you know it, we discussed earlier, you can have a different structures. So, that we can make the river or the canals is navigable, maintaining its alignment. Now, you talk about the basic way, the cutoff. Okay. So, you know from natural cases that when you have a river bend, okay, so river has bend like this, it increases the curvature, shorten the bends. After certain times, it cannot maintain more shortening of bend, because overflow happens, the flow overflow happens like this. Okay. The bifraction band covered. So, it form a head cut, chute bar. So, it start depositing here, then start making a chute bar and the head cut here, and after that it blocks the part, then it can take up this sense. So, chute cut off followed by the triggered by the flood, then you can have this. This is what naturally cutoffs happens. Most of the times when you design national waterways, we should understand this process what it happens naturally. That means, when you have the river bend, it bends grows it. After certain the bend cannot grow it, at that time the overflow bifractions happens it, followed by chute cutoffs are happening it with the triggered by the flood, that is what will carry the waters. So, then it's this part remains as a cutoff, remains as a cutoffs. So, because this knowledge we need it as you know it, sometime we have to man-made triggering this cutoff process, that is what we try to do it, whether you can trigger the cutoff process, because natural cutoffs it takes a lot of times, it depends upon to have a major flood events to have a natural cutoffs. We cannot wait till that. So, we try to make the as resemble to as the natural conditions, we try to make a artificial cutoffs following the behavior of natural cutoffs. So, the basic ideas we learn from the river systems, we try to understand the morphology of the river systems of that particular river and how the natural cutoff process happen. The same cutoff process mechanisms we artificially or man-made we try to introduce to the rivers, then river will be that's the idea. Always we should have a morphology studies to try to understand it, how this cutoff process happening in a particular river or particular river reaches from the past historical satellite imagery or any data set. That understanding is necessary to design a artificial cutoff. That is what my point to say that, and we have to understand the river behaviors. Okay. If we understand the river behavior, we can trigger that mechanisms, same behaviors with some artificial cutoff process. So, that is the reasons we do the cutoffs, improve the alignment of the river, reduce the sinuosity, shorten the river length. As it shorten the river length, it increase the slopes and reduce the flood stages. Okay. It has other effects, but let me have a these things to the. Now, if you look at how it happens it, like if you look at these pilot channels, okay. So, you want to cut off this river band, okay. You can consider the revetment and you can make a channel here, the pilot channel, and you can have a longitudinal dikes here and followed by you can have cut off revetment. So, we can consider that, or you can have a cut off like this. If you look at that, you have a revetment, you have a revetment trench, then you construct a pilot channel, you have a plug, then you have a revetment here. Now, if you look at that, what are the structures we put it to make a cut off channels? One is pilot channels and the cut off process what you are there. First, what you do it, we excavate the pilot channels, okay. That is what we do it, okay, from the downstream end, from the downstream end we just excavated the channels, okay. Then what we have, then we have a make it a side slope which is stable slice slope of 1 vertical 3 horizontals and keeping it the width of channels depending upon our navigation requirements 50 meter to 60 meters. Wider deeper pilot channels are initiated with their little length and the slope advantages. Okay. As once you make it the pilot channels, it slowly it can initiate it as the flow process it parallel trench, the trench you make it, okay, with the placement of riprap revetments. Okay. We make a trench, okay. With that trench we put the riprap, stone riprap revetment, we just put it. We have a earth plug near to the upstreams, okay. So, near to the upstreams, this is the flow directions, near to the upstreams you have the earth plug, okay. And end of these excavated pilot channels are left in a place in block the flow, okay. So, we try to look it as soon as the flood comes it plugs are designed to work off it and washed out and the revetment have been completed by the times. So, if you look at what I am telling that when you do for any river training work to make a cut of channels, we follow the two ways. We modified something and some part we leave it to river to do it. That is the reasons we have the plugging. So, as it naturally overtaps it, that is the reason the river can take care of widening a channel or deepening the channels depending of the flow behaviors during the extreme floods. That is the periods we will have the overtopping of the flocks, and that is the conditions. Once it establish it, then the flow will maintain it. The basic idea from this cutoff channel design, you can know it. We do some part of artificial thing and some part of the work we intentionally left to the river to do it. So, that it can make a regime channel or a stable channels. That is the idea is there. Like if you look at that, we make it the pilot channels, but we do not link the pilot channels to the upstreams. We leave it with a flux. So, that it is a design such a way it will overtop it, washed out. As soon as it washed out and overtop it, that flow will make it these pilot channels configurations in terms of bed slope, in terms of width, in terms of depth, it will change it, and that after certain days or in a seasons, it will come up a active channels with a modified width, depth, the slope, which is the stable things what we do it, and that is what we look at, and we wait till the plots to do that part. So, the idea as I said it again and to repeat it, that it is a two ways, we do some part and some part of the things we leave it to the river to do. Okay. And many of the time we should try to understand it, how do the river behave during the flood at that particular stretch of river systems. So, our understanding of the river is foremost requirement to have a stable channels or to make a river navigables. Now, if you look at the similar studies we conducted is a case studies we conducted for the Brahmani rivers. If you look at the rivers, you can look at these cross sections which is set up through the HACRS models, and these are the wear proposed wears. You can see that before wear and after wear, and you can see the channel depth requirement, and you can see the longitudinal profiles. This is part of National Waterways 5. This is a study we did it as group of hydrofluid groups. We conducted this study and we try to look at what is the design proposed wears, dimensions, where the locations, all we have done it with help of HACRS model, very detailed bathymetric data and the bed data, bed material data, all we integrated and solve this ones. So, it is possible nowadays with help of the mathematical models, we can know it, how we can make this river is navigable with a series of dam or the wear structures. That is the things what we have done in this case. Let us have another case studies, that is what very interesting case studies Rhine-Waal rivers in Netherlands. So, you can see the figures 1835, 1837, 1966. Okay. And looking these figures, these are the water and this is the levee, the embankments. Okay. And you can see the river width is much larger, the depth of the water is very shallow, some of the portions the depth of water is not there. To avoid that, there are the structures, if you can see that the structures are there, minor structures are there to confine the rivers. You can see these minor structures to confine the river in terms of the spur, in terms of the structures what you put it to confine the rivers. By 1873, okay, you can look at that almost 50 years, still river is confining it with the help of with a spur and also the parallel levee. Okay. There is a parallel levee with these ones. For the 1996, you can see the jacketing of the rivers happening it with both the sides, putting it all these the structures, the spurs, okay, band wear both the sides, such a way that we confine the river. This is what the history of river training works in Rhine and the Waal rivers in the Netherlands. If you look at that 1835, it took almost 130 years to commit to a river which will be navigable. So, what I am to tell is that when you try to make a river to stabilize and river to navigables having a flow depth, it is not a matter of the few years. Okay. It can take decades, it can take the century to establish the rivers. That is the idea, that is what the experience Waal rivers near the Thal in Netherlands. So, if you look at that, how much time that is that, how the step wise they confine the rivers. If you look at that 1835, 1873 and 1966, it's more than 120 years, and they try to do it confining the river in the step by step. Okay. And this is a major levee, and they want to put the levee in the structures in between, and they confine the jacketing the river in the both the sides. After 1960s, only 260 meter width of the rivers, which is necessary for the navigables with the depth of waters, they got it. So, that is what I am to telling it. When you do any river training engineering works, it is not the canal. We try to understand the river morphology. How does the river respond to this, the man-made river training structures? Based on that, the step wise we should proceed it. It may take few years, few decades to stabilize the rivers, because all the times river, as we know from experience, that each river to respond a particular river training works are the different, it is not the same. Even if you, that is the reasons we should do a series of physical modeling studies, series of mathematical modeling studies. Still we should acquire the knowledge about the rivers, try to understand what is the response of the rivers, the morphological response of the rivers for the stream flood events, the average flow events, how the morphology is changing it. That is what can take it very huge time. Okay. So, that is what it can take it in terms of years, in terms of decade, it or sometimes like a century to reach it a river which is stabilized river, navigable rivers. That is what the case studies by Netherlands. It is okay. It's smaller river with having 260 meter wide, but you see that how much of length the stabilizing the river becomes navigable, as well as the depth is increases, and could have increased the aquatic lives. Okay. The river health could have better. Also they have reclaimed the lands. So, it has advantage, it has a significant advantage to stabilize the rivers, as it may take the decades or maybe century, but ultimately we get the benefits in terms of river health, in terms of aquatic lives, in terms of getting the land reclamations can be done it, and you can understand it is a rich land what we get it, and you can have the levies things. It is possible. That is what is this case study is showing from the Netherlands. It took it 120 years. We can have a bank using groins, can have a main channel eroded considerably, and there are the removal of the isle. So, there are all sort of the problems what we in generally talk about, levee failure, the flood disasters used to happen it almost 1 decade before, but that is what is not there, because that what is control it with a navigations width and depth without determinal effect on the environments. That is what is possible, and more detail you can go it the structure wise, what type of the structures, what are the things are there. Now, if you look at the next ones is very interesting. Again this when you try to look at the rivers, okay, we can river corridors. Okay, we try to talk about not the river with the corridors. It has a floodplain, it has one space. So, idea is comes in that in a natural the reference sections we can have this. There will be a shallow main channel, it could have a natural levee, it can have a floodplain forest, it can have a floodplain forest, okay, which could be a before the civilizations there are not much agriculture development. you can have the secondary channels, and you can have a main channels. Okay. If you try to understand the rivers in this way, but what it happens in present conditions as the economic growth which we have the built up area, we have the agricultures, also we have to need it to protect that part, we need to put a permanent bank with a groins or the spot. We put the summer levee embankment, the channel which is a smaller channels, it becomes a deeper channels. We put the primary levees, bigger levee, we put it in the both the sides. We want to protect beyond of that. Okay. So, we put the primary levee, we put a summer levee, we have a groin and permanent bank supporting agriculture and built up areas, and then you have the banks beyond a river corridors which you protect other part of area not to affect by the floods. So, if you look at that, we transform this reference to present conditions. This happens in many part of the world. Okay. It's not that we leave it as a reference situations, we cannot leave it. We need a space for agriculture, we need a space for build up area, we need to have the river with navigables to make it economically prosperous. So, to look at that means we always convert from reference to present situation. What could be the present policy? How we can convert to go as natural as close to the reference sections. That is what any river engineering try to look at that. So, that whether he can bring as close as to natural conditions as to the reference sections. What he will look at, again he has to break it, because this part he can take a risk. So, the location when it was there natural levee, now they have a natural banks. Okay. They bank with some vegetation, so that it will act like a natural banks. The banks can be collapsed, but it can have a natural banks with a vegetation structure. You can have the small forest area which can also give a resistance to the flow. To maintain this is a deeper channels now, deeper pond. Okay. The secondary channels also activated. Okay. That is the idea is here, because you again have come back to that you can maintain give it the river to space. So, the secondary channels what we close it, that is what can be activated. Whenever you have the flood, that what you can take a risk to these ones, but you want to make a natural system, because you need to have this agriculture needs a nutrient supply through the secondary channels. So, if you look at that, if it is a river, it does not carry the water only, it carries the water, the sediment and nutrient, and it has a space or the river corridors. You as we go from the reference to the present situations, okay, which with a economical development like agriculture activities, deforestations and the built up areas, we can again mix up with increase this flood forest part, target the natural levee to the natural banks. You can activate the secondary channels with all these control systems. We can make it the natural channels, and this way we can go back to as natural as possible to back, because that is the basic idea happens to the any river engineering specialist, that he will try to make it go to as natural as possible. That is the reason we need to know it river corridor management, not the river management, where you can talk about these things in a sustainable way to manage the rivers. That is what the concept, and that is what I am just focusing on this. If you maintain that, no doubt you can have the navigations, you can have agriculture, you can have a built up area, you can also have the forest. All these compositions will be there, and we are managing the built up area. Now, look at how we can have a locks and the dam. Okay. So, whenever you have the dams is required to sustain the appropriate navigable depth, navigation's depth, what you need it as 9 feet or the about 2 meters. Okay. and the locks allow the ship to navigate in a river stiffened by the artificial cutoffs. So, we will discuss other part in more details like locks and the dams. Let me I complete these lectures again thanking my group of students and more interesting quote by Rabindranath Tagore ji that you cannot cross the sea merely by standing or staring at the waters. It's the same things what I am to talk about. We cannot manage our rivers without we go into the river systems. That is the idea of this course. We should understand the rivers with all this advanced knowledge, so that we can manage our river space, river corridors and river sustainable way. With this, let us conclude this lecture.